Hello and welcome. In the last video, the beginning of 4.1, we talked about what an antiderivative is. We used some sort of reverse derivative skills to find antiderivatives, and we formalized the integral symbol and how to evaluate an indefinite integral. What we're going to do in this video is really formalize some of the things that we have been doing a little bit further so that we have sort of a toolkit of rules that we can be using, even though we've sort of already been using them. So one thing I want you to notice is that in this sort of giant table here, the left-hand side is derivatives that we should already know. The derivative of some constant, the derivative of a scalar k times x, the derivative of a scalar k times a function, the derivative of two functions being added together, the derivative of x to the power of n, and then on the right-hand side, all the trig derivatives. So what I actually want you to do, just as a good starting point, is go ahead and pause the video and fill in just the derivatives. Don't worry about the integration portion yet. Just the derivatives for each of these functions above, the rules that we already know. Go ahead and pause the video and do that. So hopefully you had time to do that. And what I've done now is I have filled in all of those derivatives that we already knew how to do on the left. Our goal in this table is to figure out how those different rules tie to give us some things that we can use for integration. So I'm highlighting these integral symbols here. So what I mean by that is, let's start actually with the trig ones. I think they're a little easier to see. That if I am taking the integral of cosine of x with respect to x, so dx, what I'm really doing is saying what did I take the derivative of to get cosine? This is going to be equal to sine of x. So again, we're using what we already know and we're working backwards. If I integrate negative sine of x with respect to x, I'm saying what did I take the derivative of to get negative sine, and that would be cosine. Go ahead and pause the video and see if you can fill in the rest of these on your own. Then unpause the video and see how you did. Again, just working on the trig ones on the right. Okay, so I just set up each of these problems. If we integrate secant squared of x dx, we get tangent of x. And all of these should have the one thing that we talked about in the last video, a plus c symbol, to represent any arbitrary constant. So if I'm integrating secant of x tangent of x, what do I take the derivative of to get secant x tangent x? Well, that's the derivative of secant of x, and again, plus some c value. What do I take the derivative of to get negative cosecant x cotangent x? Well, that would be cosecant of x plus some c value. And last but not least, what do I take the derivative of to get negative cosecant squared of x? That would be cotangent of x plus c. So again, the part in blue is the derivative. When we integrate the derivative, we get back to the original function. The original function f of x is equal to the integral of the derivative with respect to x. So now we have a list of different trig rules that we can use to help us evaluate an integral. Now let's go back and look at the left-hand side of this table and use some of the other rules that we have learned so far. So again, I'm going to start by filling in each of my derivatives here. F prime of x. Actually, I'm going to come back to that one. And I'm going to say, what would I get if I integrated each of these pieces? So if I just had an integral of dx, that would just give me some arbitrary constant. That's one you're probably not going to use too much, but if I had the integral of nothing, I would get a constant, right? But just a plus c value. If I have the integral of just a number, like if I had the integral of 2, what do I take the derivative of to get just 2? I take the derivative of 2 times x. So this would just be equal to some k value times the x that should be there to take the derivative of, plus some arbitrary c value. Now the next one is important because it helps us actually rewrite the integral in a way that might make our lives easier. If we had some number times a function and we were taking the derivative, what we learned is that you could take the derivative and then just multiply the number afterwards. And that same idea holds true here with integration, since they're just inverse operations. I can actually take that k value, whatever that scalar is, I can take it out of the integral and integrate just the derivative part, and that might make our lives a little bit easier. Similarly, if I have the integral of f prime of x plus g prime of x, all with respect to x, I can split this into two separate integrals, dx plus the integral of g prime of x dx, because it might be easier to think about it or to evaluate it as two separate pieces. And then the last one, I'm going to put a star next to this one. This one is going to be the power rule for integration. And we talked about how if we were taking the derivative of something, some polynomial term to a power of n, we drop the n down and we subtract 1. And in the last video, we talked about basically what we're doing now is we're adding 1 to that exponent. So I'm going to rewrite this, nx to the n minus 1 dx. What we're really doing is we're adding 1 to the exponent, and we're dividing by that same power. So this would be x to the power of n plus 1 divided by n plus 1, and again, making sure we have some plus c value. So, and I will note that in this case, n can't be 1. It's not incredibly important, but we couldn't have something to the power of 0. That would just be a different type of term. It wouldn't be a polynomial term. So, now that we have these basic rules, many of which we were using in the last video without identifying them, let's just focus on practicing and using these rules in a way that benefits us. So, looking at example 1, I have the integral of x to the third power dx. So this is a polynomial term. So based on the power rule for integration that we just learned, what we do is we take the exponent and we add 1, and we divide by that new exponent. 3 plus 1 is going to be 4. So that means this integral is equal to x to the power of 4 over 4 plus c. I'm going to come back to number 2 in just a little bit. I want to look at number 3 because it is really similar to what we just did in number 1. So I'm going to take each polynomial term and I'm going to add 1 to the exponent. So t to the 4 plus 1, and I'm going to divide by that new exponent, which is 5, plus t to the first power is what's already there. So I'm going to add 1 to that exponent and divide by that new exponent, which is 2, minus 5 times t. It didn't have a variable, so now it gets 1. And then, of course, we make sure we don't forget our plus c. So if we simplify this, this is t to the 5th over 5 plus t squared over 2 minus 5t plus c. And here's the beautiful thing. What we could do is take the derivative of what we just found. That derivative should be this integrand piece right here. So you can actually kind of check and make sure that you're doing it right as you go. So I want you to pause the video and try and work through number 4 on your own, and then unpause the video and see how you did. So hopefully you had time to try that one out. The first thing that I'm going to do is rewrite this, and then I'm going to follow the same process that I've been following. 3x to the negative second power. I'm going to add 1 to that exponent, and I'm going to divide by the new exponent, which negative 2 plus 1 is negative 1. Minus x to the negative 1/2. I'm going to add 1 to that exponent, and I'm going to divide by what I get. Well, if I add negative 1/2 and positive 1, I get 1/2. Minus e to the power of 11. So this looks a little crazy, but remember, e is a number. A number to the power of 11 is still a number. So the only thing that's going to change here is that this term is now going to get an x. So check and make sure that part didn't trick you. It shouldn't be e to the power of 12 divided by 12 because e is not a variable. E is a number, just like pi is a number. So if I clean this up a little bit, negative 3x to the negative first power minus, if I divide by 1/2, that's the same thing as multiplying by 2. So 2x to the power of 1/2 minus e to the 11 times x plus c. And again, you could take the derivative of this to get back to the integrand that we started with in this problem. I'm going to have you try number 5 on your own as well, but I want to give you a hint first. My hint is going to be to split that fraction. So go ahead and try that one. Okay, so if you split that integral and simplify using properties of exponents, you end up with x to the negative 3 over 2 plus x to the negative second power. Remember that you can simplify these exponents by subtracting them. 1/2 minus 2 is negative 1.5 or negative 3/2, which is why we have x to the negative 3 over 2. And that 1 over x squared is the same thing as x to the negative second power. So now if I apply the power rule here, I'm going to have x to the negative 3 over 2 plus 1. Well, negative 3 over 2 plus 1 is negative 1/2. So I'm going to divide by negative 1/2 plus x to the negative second power plus 1. Negative 2 plus 1 is going to give me a new exponent of negative 1 plus some c value. And if I simplify this, x divided by negative 1/2 is the same thing as negative 2 times it. Right? Dividing by a fraction is the same thing as multiplying by the reciprocal. So this is going to give me negative 2x to the negative 1/2 power minus x to the negative first power plus c. So the two problems that we have left both involve trig. And I'm going to encourage you to pause the video and try and work through number 6 on your own. Unpause the video and see how you did. And then my hint to you on number 2, if you want to push yourself, is see if you can use different trig rules from previous courses to rewrite that integral as something that you know is the derivative of something else. And then unpause the video and see how you did. Okay, for number 6, the easiest thing to do on this problem is to rewrite this. This is the same thing as 2 times the integral of cosine of theta plus the integral of negative sine of theta d theta. Whoops, I should have a d theta here. So let's make that actually look like a theta, d theta. There we go. What do I take the integral of, or what do I take the derivative of to get cosine? That would be sine. And what do I take the derivative of to get negative sine? That would be positive cosine. And then we have plus c. All right, let's see if you were able to rewrite this integral in a meaningful way. So I know that cosine of x over sine of x is the same thing as cotangent of x. And since it was sine squared, that means it would be the same thing as cotangent of x over one more sine of x, because there were originally 2 of them in the denominator. And how could I rewrite 1 over sine? I could rewrite it as cosecant. So this integrand here could be rewritten as the integral of cotangent of x times cosecant of x dx. Now look up at your list of properties. Is there one that looks like this? Maybe it's not exactly the same, but maybe it looks really similar. So hopefully when you look up, you notice that the derivative of cosecant is negative cosecant x cotangent x. So if the only thing that's off with this integrand is the sign, that just means that our answer should be negative. If I take the derivative of negative cosecant of x, I would get positive cosecant x cotangent x. And then we're going to include our plus c. Now you might feel at this point like we have been writing plus c an awful lot. Is there a way to actually figure out what c is? And that's going to be the very last part of this video. So can we ever find the c value that's represented when we have our plus c? Can we ever find out what our constant of integration actually is? And the answer to that question is yes, if we are given an initial condition. So an initial condition just means that we're given an ordered pair, or we're given a value of the function at a particular place. With that information, we could then actually calculate what the c value is after we find the antiderivative. So let's go ahead and look at some examples. If we know the point 1, 3 over 2 is on the function f of x, then after we find the function in terms of plus c, we can plug in that point to find it. So the very first thing that we need to do is find the function with plus c, meaning we need to integrate. So we can rewrite this as the integral of x to the negative third power dx. And this is going to be f of x is equal to this. So if we use the power rule, we're going to add 1 to our exponent, we're going to divide by -2, and we're going to have a plus c. So what we can say is that f of x is equal to x to the negative second power divided by -2 plus c. Or we could rewrite this as -1 over 2x squared plus c. Now what we're going to do is we're going to use this point that we know exists on the function. So 3 over 2, that's what f of x is, when x is 1, equals -1/2. If I plug in 1, I still just get -1/2 plus c. And if we add 1/2 to both sides to solve for c, 3/2 plus 1/2 is going to be 4/2 or 2. What this means is that our original function could actually be written without plus c, because we know that in this case where we have this initial condition, our c value is 2. So in this case, f of x is equal to -1 over 2x squared plus 2. So for these last two examples, we're going to use the initial condition 0, 4 for both of them just to make the work to find c a little bit easier. But we're going to go ahead and work through these problems here. So I know that this number 7, I can take the over 11. I can rewrite that as 1 over 11. I can take it out because it's just a scalar. And then I can rewrite this as the integral of x to the power of 11 over 5 dx using rational exponents. This means that I can find the antiderivative by taking my exponent, adding 1 to it, and dividing by that. And if I add 1, which I could really just write as 5 over 5, I'm going to get this is divided by 16 over 5, and we have some c value as well. So this is going to become 1 over 11 times x to the 16 over 5 divided by 16 over 5. So if I have this double fraction situation, what I need to do is multiply by the reciprocal, and that's going to give me 5 over 176. If I multiply 11 times 16, I get 176 times x to the 16 over 5 plus c. So all of this is giving me my f of x in terms of still having a plus c. Now, if I plug in the point 0, 4, 4 is going to equal 5 over 176 times 0 plus c. So c is just going to be 4. So I can rewrite my function as f of x equals 5 over 176 x to the 16 over 5 plus 4. I encourage you to pause the video and work through number 8 on your own. And again, I'm going to encourage you to split this integral into pieces so that each term is its own fraction. So x squared over x over the square root of x plus x over the square root of x plus 1 over the square root of x, and then simplify. But see if you can work through this whole problem on your own and then unpause the video and see how you did. So hopefully you had time to get started. Here is my simplified integrand as 3 separate terms, and now you can add 1 to each exponent individually, so go ahead and do that part. So I'm going to end up with x to the 3 over 2 plus 1, which is x to the 5 halves, divided by 5 halves. So if I multiply by the reciprocal, 2/5 times x to the 5 halves, plus 2/3 times x to the 3 halves, plus 2 times x to the 1/2, plus c. And this is equal to f of x. Now, go ahead and pause the video and use your initial condition 0, 4 to write your function f. So if I plug in 4, each of those terms is going to be 0 when I plug in 0 except for c. So c is 4. So we can rewrite f of x as 2/5 x to the 5 halves plus 2/3 x to the 3 halves plus 2x to the 1/2 plus 4. And that will be our exact function. So let's recap what we covered in this video. We formalized those rules for integration, talking about the things that we were using in the last video without explicitly saying, using our derivative tricks. We practiced integration using different trig strategies, different power rules, splitting up fractions into multiple pieces. And then we talked about how if we actually want to find the C value, all we need to do is the same work we've been doing, but with an initial condition that we can plug in after we integrate to find the value for C. And then we can rewrite our function as a function that does not have a plus C in it. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.